My experiments on the Feynman Path need quite a bit of electronic and software support. The thing is, these experiments rarely require all new hardware and software. Many experiments are simply incremental variations on previous approaches, and consequently only require relatively modest changes to the controlling electronics and software. So, how does one deal with constantly mutating electronics and software requirements? For software, the problem can be dealt with fairly easily. Just use version management. In the FPath project, the Walnut software provides most of the control, and it is continuously modified as required. Each variation is simply checked into GitHub, as is, how is, and I don't need to worry about it further. If I wish to reintroduce some functionality that I had 3 experiments ago, all I need to do is pull the code from the repo and get to work copying and pasting. The situation is different with the electronics. If I design a custom board for one experiment, I am less likely to be able to really reuse it in the future. Yes, I have the KiCad designs which I can adapt, but getting a new PCB made, shipped, and populated is a time-consuming and expensive proposition. This really inhibits quick, iterative development. So what is the solution? Put lots of functionality on one all-singing and dancing board, or create a new one each time? It's not really a good way to get what you need, since you're never likely to have exactly every new bit of functionality you might wish for. Well, I think I have a workable solution. Step 1 is just to make my own PCBs using KiCad for design and the line grinder software to isolation route the traces and pads. This eliminates the send off a design and get a PCB back from some strange and foreign land 10 days later aspect of the problem. It does introduce additional complications, however. The downside is that the isolation routing cannot do fine details like really thin traces very well. At least my CNC mill doesn't have the accuracy for that. Isolation routing also hates complex boards. Lots of things you can easily do in a design with a PCB source from a board house, you really have to work at when isolation routing. For example, it is problematic to run a trace between 2 pins. Yes, you can do it, but the setup and care you have to take really increases the time and failure rate. Ultimately, it is easier just to use jumper wires to get the traces from one side of the board to the other. Effectively, this means the more complex the design, the more problematic it becomes. I'll show you what I mean. Here is an example of a board I designed to manually control 3 stepper motors. I designed and built this as a practice piece. The idea here is that the microcontroller, in this case a BBC microbit, outputs a pulse train. The pulse and direction signals can be directed to any of 3 motors, which then get the proper steps from the 3-stepper motor driver chips. A momentary switch controls the on-off and direction. A second momentary switch can change the speed up and down. The board looks fairly clean from the top, but underneath it is a rat's nest of wires and ugliness. The board took no little amount of time and effort to make, and I was deeply unhappy with the result. Also, as a unit, the resulting design was only good for one thing: the manual control of 3 mid-voltage, 10 volt or so, steppers. The specificity is problematic. For example, what if I wanted to drive low voltage steppers? The 3 volts they require cannot be provided by the existing driver chips. What if I wanted to incorporate a relay or a sensor switch? The design would have to be reworked and the board completely rebuilt. It occurred to me that a lot of these controls are separable. A momentary switch can be a separate component on a separate board from the motor driver carriers, which in turn are separate from the board which mounts the microcontroller. It's a modular system. These boards can be strung together like beads on a string using simple, commonly available electrical connectors. Thus, if I need a low voltage stepper driver, I can simply connect it in. I won't show you the wiring montage. It's all just plug and play. Let's just assume it got done. On the screen you can see, starting from left to right, the power distribution board, an on-off switch for the stepper power, a microcontroller breakout board, a fan-out board to duplicate certain signals, a momentary switch for the motor direction, and a stepper motor driver board. Here you can see the motor being driven backwards and forwards. If I need to control a second stepper motor, I simply add new modules. Of course, the code in the microcontroller needs to be updated to facilitate this, but that is just software, and is much easier and quicker to turn around than creating an entirely new board. Here, I'll show you. I will add another stepper driver module. This one is for a 3-volt stepper driving a sled cannibalized from an old DVD drive. I can move each stepper motor individually. Here is the larger stepper and the DVD sled moving back and forth. Now, if I need a relay or a sensor, I just design a new modular PCB, wire it in, and I'm off and running. The software has to change, but this mechanism is far better and cheaper than creating an entirely new board. Plus, when I move on to other experiments, these modules can just be dismantled and reused. Before we move on to other things, let's talk about a few of the boards individually. In future videos I won't do this, but in this case it might be useful as it does kind of illustrate the philosophy of the system. This module is the power distribution board. I will need about 10 volts for the stepper power and 3.3 volts for the various CPUs and driver chips, so something has to supply this. Rather than designing a power system from scratch, I just went online and purchased a PCB designed to provide 3.3 and 5 volts to a breadboard. It is a simple matter to design a footprint in KiCad and mount it on an isolation routed PCB. I moved the barrel jack down here for the V-in voltage. It needs to be between 7 and 10 volts. A cheap variable power unit plugs in to provide the source power. The terminal block here passes the V-in back out for other uses. There are 4 3.3 volt terminal blocks and a spring terminal block also with 3.3 volts and ground in case it is needed. On the left-hand side is a 5 volt output terminal block and a similar spring terminal block for that. There is an on-off switch and a LED. The power supply design incorporates some nice regulators which have current fallback in case of overload. All this is very inexpensive. I could not even begin to purchase the components for what this small power supply part cost me. Not to mention the time it would take to design and test such a circuit. I do not want to reinvent the wheel. I just want power when and where I need it. Looking at the underside, you can see that the traces are simple. A single-sided circuit board like this is easily within the capabilities of an isolation routed PCB, or even a handmade perf board, and is easy and quick to make. The next PCB I want to show you is a breakout board for the BBC microbit microcontroller. As before, I purchased a commercially available header for the microbit designed for a breadboard, created a footprint in KiCad, and designed a board which presents the I/O pins in spring terminal blocks. This board is very simple and quick to make. Here is a look at the underside of the board. Literally nothing amazing here. This design is simple and easily within the capabilities of an isolation routed PCB. I should note that the BBC microbit is not really my microcontroller of choice. A while back I got sidetracked onto a fun project creating a bare metal C++ library for it and just decided to use it for this demo. The library is called YakIO and the link is in the description if you're interested. The point here is that any microcontroller could be used. For example, an ESP32 or any sort of Arduino could be implemented in the system simply by building a module for it and reworking the software. For the record, my microcontroller of choice is a BeagleBone Black running Linux. I have this device networked back to a Windows 10 PC, and together they form the client-server architecture of the Walnut control software. Note, I did not design and make the breakout board here. That is a commercially available product. I did, however, mount it on the perf board. Here is a 10 to 40 volt stepper module, a momentary switch module, a power switch module. There are lots of others I won't go into just now. Here are some connector wires for power and some for signals. I have a number of these in pre-configured lengths, and they greatly simplify connecting up a new electronic driver architecture. The point here is that everything is modular and that most of the heavy lifting is done by slotting commercial components onto simple, easily manufacturable boards. The connections are either terminal blocks for power or spring terminals for signals. Any new components can simply be mounted on a new module and swapped in as required. I find this idea to be a great improvement over having to rebuild a new board for each idea I want to test. Let's talk for a brief moment about the construction of the modules themselves. You have no doubt noticed the little black bars running down the side of each module. These are 1x10 Lego bricks, and the PCB is attached to them with small M2 wood screws. The holes in the PCB are carefully positioned so they are right on top of the studs in the Lego brick. The width of the screw spacing is such that when the two Lego bricks are screwed in place, they will fit on a standard Lego plate. The attachment plate is also Lego and it forms a type of rack mount panel. Lego bricks are easily strong enough to hold the modules in place, but they can be easily removed when disassembly is required. Believe me when I tell you that the Lego company has put an insane amount of R&D into getting this force exactly right. It would be crazy not to take advantage of it. I use Lego for lots of experimental apparatus like this. They are a wonderful, inexpensive, consistent, and accurate way of firmly positioning small parts. This is discussed in more detail in the Steggo project. A link is in the description. That's basically the modular electronics design philosophy for the FPath project. Make every reasonably separable function into its own module. Make the modules use one of two standard connectors and assemble what you need when you need it, a lot like Lego bricks. Note that PCBs themselves are a tiny bit less than the length of a 10-stud Lego brick, and the width of the PCB module is a tiny bit less than the width of an 8-stud Lego brick. This makes it possible to mount the modules closely side by side. The smaller modules are sized as a 10 by 5 rather than a 10 by 8 like the larger ones. This provides a pretty versatile rack mount system. As long as the modules are 10 studs high and an integral number of Lego studs wide, they can neatly be placed in whatever order you wish. Note that the connectors are never placed on the longer side, always on the top and bottom. This makes the modules fit nicely together, and the wires can be laid horizontally underneath or along the top edge. There are a few other design things like that, but in general it's a pretty simple system. Since it might be useful to others, I decided to formalize things and write it up and propose it as a standard. I call it the SteggoRack Standard, which is an homage to the EuroRack Standard, so beloved of amateur music synthesizer community. Links are in the description. Well, that's how the electrical control system is constructed in the FPath experiments. I just thought you might be interested to see it. Thanks for watching, and see you next time.